Rust's pragmatism has focused valuable attention on memory management, and introduced the masses to many things taken for granted in functional languages for decades. For example, what Rust calls enums, or algebraic data types, first appeared in the language Hope in the 70s, and has been an absurd omission from mainstream languages ever since. As for memory, mathematicians have neglected this sort of operational detail, since from their perspective it is irrelevant. And yet, as Rust aficionados never tire of pointing out, memory bugs make up a considerable proportion of correctness issues in software. Both Microsoft and Chromium, working largely in C++, found 70% of their security bugs are memory-related. We must credit Rust with one major achievement. The ownership experiment has lit a proverbial fire under researchers to take memory seriously. It has been tricky to nail down exactly what Rust does, since it evolved orthogonally to theory, and does whatever it wants, which apparently was borrow-checking in a separate pass that generates and solves constraints. Sadly, blindness to theory creates weirdness, unsoundness, and causes it to miss the more useful half of the ownership linearity adjunction, as we shall see. Constraint-based approaches are considered a cop-out, and if constraint solving really is necessary in a type system, then in my opinion you've got the wrong idea. Type-directed solutions are simpler, faster, and make better error messages. A recent successful type-directed formalization of Rust, called Oxide, uses region-based aliasing. Lifetime subtyping sounded more intuitive, and indeed was tried first in Rustbelt. But in being extended to non-lexical lifetimes, Rustbelt's model used continuation passing style, and lost the ability to reason with the source-level language. Our best model is regions. They separate data lifetimes from function lifetimes. Both form a tree, but decoupling them allows, for example, to construct and return memory up the call stack. Regions are an extension of stack memory, freed from the rigid structure of function calls. Incidentally, intermingling function return addresses with data is a historic mistake in the ABI. The call and data stack should have been separate, both for performance and security. That way data can be stacked uninterrupted across function calls, and the processor will never interpret data as a return address, instead having an easier time predicting the next instructions. The ancient with-style functions, including alloca, deserve attention. They take a function of a temporary resource, which is allocated and deallocated by the same wrapping function. That is so easy that it is worth optimizing by pushing down the freeing operation so it happens as soon as possible, and make it completely safe by preventing any local memory from being returned. With an ownership-aware type system, this is region memory in an equational setting. Optimal memory management, however, is devilishly tricky and defies direct classification by regions alone. Memory is the sort of barely relevant low-level detail that defies automation and obfuscates algorithms for no profit. At the same time, considerable performance can be won or lost, and horrific bugs are at risk. Performance usually calls for arena allocation, and linked or circular lists, both of which regions don't really address, although they can hide these operations behind a malloc-free interface. Regions do, however, almost perfectly handle fractional ownership. Allow me a brief aside into memory management principles more generally. First, ease off pointers, and also memory. We'd rather not deal with any of that, and writing non-recursive, non-memory functions is very often possible. When writing to memory is necessary, you can often do it in small driver functions that isolate the dangerously unclean operations. Second, return struct by value more often. By value or by copy usually means in registers, so is much faster than being read and written indirectly for an extra pointer on the stack. Sadly, the x86 ABI, when passing a struct larger than 16 bytes in and out of a function, will force it to be written to memory, and generally uses much less registers than it could. This is still the best thing to do, as long as you know when the disgusting ABI will force a copy of a prohibitively large struct. Functions should be static by default, and inlining always eliminates call overhead. Naturally, we'd like a better ABI, and also subtyping on structs. But regrettably, Rust made no attempt to improve this state of affairs, and largely repeats the mistakes of C via LLVM. Anyway, small memory objects should not be explicitly memory managed. They are error-prone, easy enough for compilers to manage properly, and generally not worth our time. If they fit in 128 bits, they are passed in registers. Failing that, note that copying a few hundred bytes for a pair of SIMD registers is extremely fast, so relocating things can be cheaper than messing around with pointers, and also leave fewer random holes in stack memory. Compilers rarely generate perfect code anyway, so there's little use in obsessing over these imperfections. And finally, the key insight is memory management is a distinct concern from data transformation. It can and should be separated. As for our tools, automatic memory is available via the stack, by default 8 megabytes of local function data and return addresses, pushed each time a function is called and freed when it returns. The structure of this data stack is tightly coupled to the function call structure, and although there may be chances for memory to be partially freed and reused, in practice stack memory is leaked until the caller returns, which can take a very long time. We are discouraged from allocating large data on the stack. Stack space is limited, and exceeding it will cause the famous stack overflow as the kernel notices you try to read or write past the virtual memory pages allocated for stack space. An interesting suggestion is that the kernel should page in more stack space as required and make us immune to overflow, relatively for free. So the question of how much work we can squeeze out of stack memory becomes interesting. Of course, the mathematicians have us covered here, and the canonical construction is the hylomorphism. That works over an arbitrary functor as the equivalent of an anamorphism fused with a catamorphism, and makes perfect use of all the memory being stacked, possibly in parallel. Quicksort is a great example. The functor is a binary tree that we unfold and then flatten, using the input list as a seed. Hylo is a standard function that I copied here. See how the Hylo recurses by unfolding an entire tree in memory using our split function, then retraverses it with merge in the reverse order, unwinding the stack and concatenating the result list. This is all mediated by the binary tree functor, and is a crystal clear way of encoding our algorithm, drawing on the elegance and perfection of category theory. Hylos are occasionally useful, but anamorphisms are more common since most programs end up unfolding a byte string to print or write to a file as binary data. Even if you are reducing to a value eventually, it's usually possible as a fused left fold rather than a right fold, noting that fold R is the list catamorphism. Now, yes, depending how this is compiled, it probably can still overflow the stack and probably still intermingles local data with return addresses, even though the ABI is irrelevant in the middle of this construction. Furthermore, on x86 we would like to use the fast push and pop instructions, but they only work on RSP, the stack pointer. Compilers could easily do a much better job here, and frankly they should have a built-in understanding of recursion schemes like the hylomorphism. So much for the stack. If we want maximum flexibility and must write intermediate data to memory, we reach for heap memory. That need usually arises when we need long-term random access to some carefully crafted structure. Stack memory grows downwards, and in the past grew towards the heap, which started at the end of the program's data segment. The SBRK syscall would increase the program break and gain more heap memory. This rigmarole is nowadays deprecated thanks to virtual memory, which we instead allocate from the kernel via mmap. Mmap is for allocating large pieces of memory, say at least a dozen pages, each 4 kilobytes. But since memory is virtually allocated page-wise by the kernel, you can even allocate unused terabytes of addressable memory that won't all map to physical memory, because they are paged in dynamically. System calls are slow. They must interrupt back into the kernel, and mmap also does some internal bookkeeping for pages. Page faults occur on unprepared pages and are basically a hidden system call. So we turn to malloc to handle quickly suballocating from mmapped arenas for us. In a sense, all memory is arena allocated. Malloc lets you pretend this isn't so, but unfortunately it has no clue what you're planning. You give it a size T and tell it to get on with it. The allocator must be ready for everything. It represents both a thankless task and a fascinating academic problem. Implementations have ample scope to be clever and deploy different strategies for different sizes. The better mallocs like JE-malloc will pack allocations of the same size together and use a bitset to mark holes in there, making the very reasonable assumption that most allocation sequences will use data of similar sizes. Free usually does the absolute minimum by appending the chunk to a free list in the hope it will be reused instantly. Then the expensive operations only happen during allocation. This is all rather opaque and only loosely connected. malloc is incapable of doing garbage collector-like reorganizations of memory, and inevitably fragments over time. Accessing local memory can be orders of magnitudes faster than accessing random memory all over the place, so locality is always a major concern. Since only you know exactly what you're planning with the memory, only you can optimally manage it, and any use of malloc is necessarily suboptimal. If for no other reason, then you could inline a small fast path and frequently avoid the function call overhead. Anyway, the important memory objects to get right are the recursive ones. The arrays, the trees, the linked lists. Most of the time, that goes through standard libraries. The remaining portion of the time, either a recursion scheme or a bump allocator will be ideal. Small, short-lived objects should be passed by value, not by pointer or const pointer. Even if the idea is to be forwards compatible with future larger structs, a better way of doing it is making a new function that aliases into the first. Backing up to the beginning, new programming languages are instantly faced with a choice of gargantuan importance. Should they follow mathematics or follow the silicon? Is it not crystal clear which path has a future and which is doomed to be a historical hack? A solid theory can easily degenerate into practical hacks, but blind hackery digs the sort of hole that you can never climb out of, especially once you have users with pressure to remain backwards compatible and quickly respond to bugs in a half-baked amalgamation of overlapping ideas. We must place special emphasis on fusion, since it bypasses memory by avoiding intermediate data and is a massive optimization, but neglected by silicon-oriented languages. Fusion is only consistently possible in pure functional languages leveraging an equational theory. Programming should and will be about equations, not manually fiddling with mutable registers and memory addresses. In this regard, category theory is the most valuable programming tool we have. It is the study of composition and code reuse. Pretending it doesn't exist only causes one to make avoidable mistakes or to miss obvious connections. Most of us initially learned programming through trial and error. That was maybe necessary, but leaves us with dangerous ideas about how to get things done. Not reading documentation and repeating avoidable mistakes is basically standard. You may have noticed, however, that forcibly wading through problems experimentally at some point hits a wall. Mastery is about predicting problems and adjusting before wasting time in dead ends. Writing programs is easier than modifying them, but first attempts in unfamiliar territory are fraught with peril. In the beginning, I wish for results quickly. In the end, all I care about is correctness and control. A mathematically justified approach is the only future-proof strategy. Regrettably, functional languages have invariably managed memory using garbage collectors. There, either they do reference counting, which is fine for sufficiently large objects, or tracing collection, which frees infrequently, but when it does, has to scan all live objects in the region from some roots. Needless to say, that is painfully suboptimal, and comes with a fat runtime. But none of that is necessary. It's essentially a skill issue. Perhaps the most important ignored open problem in computing at the moment is attaining both principled correctness and optimal performance. In the meantime, it's hardly surprising that pragmatism and aggressive marketing has managed to capture the public's attention, who can hardly be expected to understand how much potential lies just barely out of reach. Rust's raison d'être is the ownership model of memory. This type here means a reference to a type T which is valid for a lifetime A. Lifetimes are ordered by a subtyping relation, pronounced A outlives B. So B is a subtype of A and can be converted to it automatically. References to references are valid as long as B outlives A. There is also a longest lifetime, static, such that all other lifetimes are subtypes of static. Now, Rust wanted generalized algebraic data types, where a type constructor is valid for all A, but only inhabited for certain A. GATs are well understood in type theory, but Rust had to settle for TA being a constrained type. It is a valid type only for certain A. Now, there are two ways to interpret for all A T of A to U32. For all A means this type is invalid, since TA doesn't work for all A. Or it means for all A where T of A is valid. Now, this weirdness is not necessarily fatal. Here's an example with lots of borrowing. We begin, for fun, with a double reference to the unit value at the longest lifetime. Actually, it's to expediently obtain some lifetime subtyping. Then, foo takes two parameters, a reference to a reference of unit type with lifetimes A and B, and a reference to some type T with lifetime B. It produces a reference to T with lifetime A by returning V unchanged. So we're just playing with types here. Then bar takes a reference X with lifetime C and returns a static reference to T. Now, if you're paying attention, that should be impossible. Lifetime subtype in the other direction. This is in fact a very famous example, one that has been reported to Rust and unfixed since 2015. Can you spot the problem? The trouble is foo's type requires A to outlive B, but that constraint does not appear in the type of F. You see, Rust sort of has subtyping, but not in any principled fashion. With subtyping, function input types are upper bounds and output types are lower bounds. Because the direction of subtyping flips when going for a function, so-called contravariance, and the type of foo is wrong, we're able to cast a local lifetime to static. Naturally, a hack was implemented to fix this, one reported example, but the problem persists despite being a priority for over a decade. Rust's subtyping uses coercion sites rather than true subsumption, struggles with trait objects and contradictions with OOP features, attempts to infer variance amidst attempts at invariance, and is basically completely broken at higher ranks, which is troubling since higher rank functions are so strong and so useful as to appear everywhere in languages that support them cleanly. The point of this demonstration is to motivate a more theoretical treatment of region-based memory, where we can judge the value of the new ideas, unpoisoned by any irrelevant brokenness. First though, safe inbounds array checks deserve immediate attention. So-called safety by runtime panic is a funny marketing ploy, but consider the real solution using dependent types. Vector is a type family indexed by a natural number. The length is statically known as a function of some arithmetic. Indexing this vector is done with a finite natural. In this way, inbounds access is always guaranteed, correct by construction. Notice fin and nat are viewed constructively, although they will of course be compiled to machine integers. Making programs correct by construction is the default approach, where dependent types are standard, like in proof assistance. They can encode arbitrary constraints, and complicated types may be interpreted as propositions, considered proved if you manage to construct an inhabitant of that type. Unifying values with types, and so making types first-class citizens, allows perfectly handling generics and macros in the same type-safe uniform way as values. Dependent types have so far been perfected for use in theorem provers, but languages like Idris are bringing them to general-purpose programming, and there is no doubt they will become standard in all programming. Now, Rust is extremely unlikely to gain dependent types. That requires a principled type system and respect for theory, and anyway isn't the sort of thing you can easily tack on later. So, to make sense of memory, we better turn away from underspecified collections of features. A great tool in category theory is that one can always flip the arrows and study the opposite category. That yields an interesting dual construction and additional insights. So it is with borrowing. The flip side of that coin is linearity, and in fact they form an adjunction. I'll spare you the deep theory here, because although it is extremely valuable and exposes deep connections, if it's your first time, it may be counterproductive. Linearity is actually the more studied older half of the adjunction, especially with regards to dependent types, where quantifying over resource usage is necessary to ensure type-level values exist only to specify behavior, and are not present at runtime. This has been extensively practiced as quantitative type theory in Idris, where quantities oversee consumption of resources through type-level protocols, like unique file handles, channels, network connections, session types, database access, and unique ownership of mutable arrays. Historically, Haskell has had immense success in forcing resource uniqueness with a monad, but modeling resources with quantities is more powerful and lighter. It will be most instructive to examine quantities in the practical context of the research language Granule, which implements graded modal types and allows fine-grained control of both usages and ownership. A linear value must be used exactly once. Both duplication and discarding is forbidden. We can be perfectly precise about resource usage using graded modalities. Here, dup's type promises to use X at type A exactly twice. The square brackets introduce graded modal types and corresponding values. You can also specify intervals. Here, the first parameter is used between 0 and 1 times. There are plenty more examples in Granule's repository, showing how reasoning about resources at the type level allows us to accurately describe cross-thread aliasing, file handles, session types, network protocols, and even effects. Mutable arrays, for example, can be made safe for in-place updates using linearity via a with function. Here, the only way to get an array is inside the array A at grade 1 to an unrestricted B function, which returns a guaranteed unrestricted value, and the only exposed functions accepting an array are linear, so there is now no way to duplicate an array. Types encoding function behavior in this way is natural and can do the majority of what we want, but this signature is not ideal. There is one major irritation that has plagued both Linear Haskell and Idris. The scheme falls short when you want multiple arrays simultaneously. The higher order function controls the lifetime of a single array, but kills all linearity. Linear Haskell has struggled horrifically with this and come up with a few hacks. There, they additionally suffer from only quantifying on the arrow and lacking Granule's fine-grained control. Notable attempts involve phantom type parameters to encode a region, since the type system complains if a type variable escapes its scope. But that is ugly, and anyway more fragile in a dependently typed setting. Also notable are the alloc besides functions that try to reuse an existing array as a uniqueness proof. Basically, with array forces a type bottleneck that is too limiting. Maybe there is a solution, a way to enforce a grade on the new array without interfering with anything else. As we shall see, the ownership model requires existentially quantifying on identifiers to track provenance, so perhaps that could work here. Although we are very reluctant to add anything unless absolutely certain it's necessary. To discuss Rust intelligently, we must wade deeper into the swamp. Instead of types restricting functions, the flip side is a function restricting its callers. By making usage demands on the inputs, we can encode Rust-style memory regions. To start, we can require values to be unique. The asterisk in Granule indicates a unique resource. So to invoke this example move function, we must give it a provably unique color. We're allowed to move ownership to X, but we are not allowed to duplicate the input in any way. Next, we need a way to swap in and out of uniqueness, for example using share and clone primitives. The exclamation point is the of course modality, allowing I to be copied at will. Since it is graded, the parameter must appear within square brackets. This could be made more ergonomic, but that's a small thing. Granule wants to explore how far linearity by default can take us. Float array is unique throughout the start of the program, as enforced by new float array returning a unique float array. Is the type as used by Granule internally. Share gives up on uniqueness guarantees, returning to normal value management. Clone makes a deep copy. That's a straightforward way to guarantee uniqueness of a new object. We may prefer to avoid that by escaping uniqueness in more controlled ways. Fractional borrows are the graded form of non-uniqueness. The with_borrow primitive allows temporarily converting unique values to borrowed ones, then split can create two borrows out of one. Later join must return everything, so split and join form an isomorphism. Mutable borrows have full access to the value, so may write to it. Immutable borrows have only fractional ownership. So armed, we can implement a safe and general interface for mutable arrays. Here's a complete example from the Granule project that splits a unique mutable array into two and concurrently sums the result. We can even check it ourselves. The contents is hopefully self-explanatory. It's working on a unique float array and a unique pointer to a result float. That is all well and safe, but of course we may wish for more. For example, the push and pull operations could automatically move grades across products. Also here, identifiers for each mutable reference are existentially quantified, so the types can distinguish different borrows at different types. There may be alternative approaches. This one is a little odd, but not objectionable so long as it stays out of the way. A final point of interest is there are no references to references in Granule. Graded modalities are more powerful. And haven't we all felt that pointers to pointers are an aberration? The theory this time came with a fairly complete practical implementation for experimentation. It does a great job of being safe and carefully motivating each complication. It is not entirely convincing, however, and didn't have the time to attempt an automatic operational interpretation of linearity or ownership. I have no doubt, however, that most of the time under these descriptive equations, memory could be perfectly handled automatically. We have seen the dark side of theory, namely incompleteness and having to wait for ideal solutions to be figured out. There are too few researchers. But mark my words, going your own way and implementing whatever seems convenient is committal and dangerous. Compiler developers take on immense responsibility. Everyone seems to think they can take shortcuts and then fix things later, but every time, reality asserts otherwise. You can invest some time to do it right the first time, or spend much longer wishing you could crawl out of the hole you keep digging. It is trivial to add things, harder to understand what you're doing, and nearly impossible to remove features and do things properly later. It is time to cautiously set one foot outside the ivory tower and survey our messy reality. Starting with dynamic linking, because the trade-off with static linking is one of the most misunderstood things online. Rust circles are sold on inlining, aggressive monomorphization, and rejecting dynamic linking. They say faster executables means more specialized code means it's faster. That is the case inside hot loops, but only so long as the code still fits in the cache. Otherwise, and in general, it's wasting space and rather insidiously evicting data either from itself or other programs on the system, in a way that does real harm but won't be measured when benchmarking only the Rust program. Anyway, gratuitously wasting disk space and live memory is not brilliant. Behind this deceit is neglect of dynamic linking, ABI stability, and modular design principles. Imagine if printf wasn't shared between every C program on your system, or if massive libraries like GTK or Qt or LLVM were partially duplicated for multiple apps. It doesn't just waste memory, it trashes the cache and costs real performance. Executable footprint is always important, especially on the web and especially for a systems programming language. Swift deserves a shout out for taking this problem seriously. Swift is Apple's language designed to run on mobile devices where wasting time accessing memory all over the place also wastes battery life, so is doubly unacceptable. They want all programs to link with system libraries and maximize code sharing. It's not that hard. The language must provide a stable ABI and forward compatibility. That is vital for maintenance anyway and must be solved early, otherwise this sort of thing never gets fixed. Swift has similar features to Rust, but uses a resilient layout that must be queried through witness tables. That allows generic functions to handle substitutions. The effects are to massively reduce code size, speed up compile times, allow generic code to be dynamically linked, and everything easily updated, while remaining compatible with future changes. It also solves most of the object safety problems that plague Rust. And you could conceivably do better, sometimes avoiding witness tables by specializing functions to have multiple entry points, for example. So inlining within hot loops can bring serious performance gains, especially if it enables fusion. Unrolling loops can hide some latency if there was a dependency chain stalling the CPU, but is often overdone. Outside of loops, the difference is negligible. I have criticisms for the way ELF files are linked, especially with the flat hashed namespace, but generally it's well enough designed and has protocols in play for forward compatibility. You have the option to spend time at startup doing text relocations, so at runtime there is zero overhead for using dynamic libraries. worth doing inside loops, and maybe theoretically possible in parallel with other startup operations. Anyway, lazy relocations via the PLT aren't that expensive, and the real work isn't going to be jumping between functions across dynamic libraries, but hopefully instead optimized for SIMD on the local architecture. The lost performance due to disinterest in dynamic linking is the least of our worries, compared to the gaping security hole this creates. You see, bundling is a well-known taboo for package managers, where bundling is any of statically linking against a system library, shipping your own copy of a library, or including snippets of code copied from a library. Obviously, bundling is extremely tempting for inexperienced or lazy developers, since it hides dependencies, obviates the needs for package management, and allows localized hacks. Suppose a security flaw is found in the library D, and a fix is released immediately. Package sets that take security seriously can upgrade their packages within the day. Now, for programs dynamic linking with D, the update is free and instantaneous. For static linkers, you have to rebuild the entire program. If you're on Gen 2 and keep object files around, that is of minimal inconvenience. But for everyone else, and especially users of the notoriously unrushed Rust compiler, in practice patches are delayed, often for months. Worst case is a bundled copy of D where the dependency is invisible and potentially modified. Then users don't even know they are running vulnerable software. Static linked programs receive performance updates more slowly and waste space on disk and at runtime. You aren't even absolved of version control, even if you are willing to copy the same library multiple times for different transitive dependencies, since there are increased risks of symbol name collisions. Basically, when you see a bundled dependency as a serious package maintainer, you have to rip it out. But first, you have to figure out what version it is, whether it was modified or forked, what to diff against, and then it must be patched and tested, and all of that represents a harrowing waste of time. The fact most Rust programs do this gleefully is obscene. Many vulnerabilities that get exploited were known and patched, but the patch wasn't applied. VulnCheck recently reported 32% of exploited vulnerabilities were 0-day. Scary, but as you see, it's much more likely and much dumber to be caught with unpatched software. Attackers have way too easy a time learning well-documented vulnerabilities, and can sometimes even directly copy an exploit and check if it still works. Even if you aren't the target of malicious attacks, unpatched software is slower and buggier than necessary. One often sees praise for Cargo, Rust's build tool. I suppose this happens by comparison with C's non-existent package manager, or perhaps Python or Node.js stuff. Compare it to Nix, however, or even Haskell's Cabal, both of which predate it, and you realize it's rather weak. Nix in particular provides truly hermetic, reproducible builds, and Nix doesn't deserve praise. Cargo uses a flat namespace and absolutely does create the dependency hell it claims to avoid. There are astounding amounts of bloat, half-finished, deprecated packages that duplicate work, and associated supply chain weaknesses. Here is a clownish repository doing satirical commentary on a Hello World game set up in Rust. It is tuned to highlight Rust's worst qualities, and there's an undercurrent of terminally online culture war that I don't pretend to understand. But it isn't wrong. The build system can have runtime errors, and run arbitrary build scripts. This is another security hole, and worse, just loading proc macros into an editor can execute arbitrary code. You get all the trouble of a centralized repository like typo squatting and hijacking of existing crates. The only defense is trusting the maintainers. The CV, or common vulnerabilities and exposures, are unfit for language ecosystems. CPE wasn't designed to identify packages. The process can't be automated due to lack of consistent mappings and blindness to transitive dependencies. Tons of work is generated, and it's only correct about 20% of the time. It's reviewed by non-specialists and sometimes weaponized to make developers fix bugs. The common vulnerability scoring system is also basically meaningless for libraries. This paper examining security risks in Rust specifically provides some choice quotes. In terms of vulnerability density, we observe a continuous upward trend at the package level over time. but a decreasing trend at the code level. I interpret that as the memory safety working, but the hopeless static linking packaging system starting to weigh on people. Vulnerable code contains statistically significantly more unsafe functions. So perhaps shoehorning memory management into a region-based model isn't always that easy or that great of an idea. Even buffer reuse over a loop isn't allowed. The majority of the vulnerabilities in the Rust ecosystem relate to memory safety and concurrency issues. Well, how unfortunate. At least there are fewer than in C++. Rust has little to say about program behavior and an unsound type system to boot, so I hope nobody believes it can solve security. Not even proof persistence would make that claim, and there you work with arbitrarily precise types. When researching Rust, the amount of overpromising, underdelivering, and misleading information has been exhausting. I've collected purported advantages. These lists certainly look impressive on the surface, so let's take a look. Generics then. There is heavy syntax, no higher-kinded types. They form a second-class hacky language. Compares very unfavorably to dependent types. Traits. There are no higher-rank trait bounds. There are embarrassing object safety limitations and dodgy subtyping interactions. Generally, they are worse than type classes, which are themselves suspicious. Algebraic types. While they're below FP standard, there are no GATs, there's weak deriving and noisy syntax. The result. It's not actually a monad. It's very unergonomic compared to Haskell's maybe or either. Cargo. We have seen this is one of the weakest aspects of Rust due to lack of modularity, the static linking, and the flat namespacing. There are too many overlapping packages, half-made, abandoned, bloated, insecure, often pulling in forests of transitive dependencies. Tooling is good, well, not compared to functional languages and their principal type systems. External checkers like Miri shouldn't be necessary to detect undefined behavior. Memory safe. Except when one doesn't feel like it, or regions don't model our desires. Sound systems don't need escape hatches. Type safe. It's not even close to the standard of a random typed functional language. Runtime safe. Memory leaks still abound. You have to use external tools to detect undefined behavior. Some safe things are actually runtime panics. Zero-cost abstraction. It is a runtime and binary size exaggeration. Most of these generate massive LLVM and hope it simplifies. For example, a common first instinct in Rust is to create wrapper objects implementing drop and automatically calling the cleanup function. That is a lot of annoying boilerplate that doesn't always disappear. Minimal runtime. Absolutely not. Binaries are extremely fat and many packages are duplicated. There's not even support for custom allocators. Security. Really bad track record due to static linking, bundling, and dependency management. The type system is unsound and incomplete. Incremental builds. It's not very incremental. Macros. There are two systems and a deriving mechanism. Both are broken, both a separate language slapped on top. Unclean, unchecked, unergonomic, with poor error messages. One of them does regular expression like pattern matching. Documentation. Seems fine, but Haskell's Hoogle is still unbeaten for API discovery via types and fuzzy names. Performance often loses to C, often gets in the way of optimal memory strategies. Elegant? No. Production ready? Constant ecosystem churn and additions, break changes. Fearless concurrency. The meaningless statement. At face value truer in the functional world where transactions compose. Async and await. Two parallel universes of code. Every dependency brings its own runtime. Simple I/O operations require understanding pinning, wakers, futures. Await points are cancellation sites, so cancel safety is now also a concern. Bounds checked safe. It degenerates to runtime panics plus a runtime cost. Good error messages. Not really, but whatever. Pattern matching. Incomplete versus the functional world. Can't match values, and it sort of does nested matching, guards and all patterns, but with heavy syntax. System programming. Yes, with lots of unsafe. The main point is many of these features have been mastered for decades in functional languages like Ocaml and Haskell. I understand the allure of Rust. Rare is the language that attempts to give both low-level control and safety. That is so cruelly lacking nowadays that any promise in that direction will gain attention. Attention is further seized by success stories about Rust rewrites. Discord in 2020 identified Go's garbage collector cycles were killing performance. They report the initial rewrite to Rust had the same performance, and then by further swapping from hashmap to btree map, swapping out their metrics library, and generally reducing the number of memory copies, they were able to improve performance beyond that. Ripgrep swapped to Rust and gained tons of performance. This is the gold standard for rewrites apparently, although everyone seems to miss that the performance gains are thanks to using a completely different SIMD algorithm, inspired by Hyperscan of the likes I've discussed before. SIMD is obviously much faster than Scalar, and ripgrep actually leaves many SIMD techniques unused. Rust itself was originally written in Ocaml, which interestingly and very famously has the only correct implementation of a module system of any language family. Modules and interfaces must have a statically checked many-to-many relationship. Ocaml modules may be functors, so you can parameterize them to generate specializations. Formally, M and N are modules, A and B are interfaces or headers. N is a new model implementing B using an unspecified implementation of A. The point is the source code M implementing A is denied to N, and in a sense irrelevant. We have complete control over exposed APIs. Internals of M may freely change, and you can freely swap M out for X. In a sentence, transitive composition allows structurally equivalent modules to substitute for each other. Incidentally, this is the semantic foundation for a type system. Implementing modularity properly is not inherently difficult, but astonishingly few languages do it properly. It seems Rust wanted to follow in Ocaml's footsteps, but something went wrong. If I had to guess, the non-type-directed ownership experiments made pretending to have a solid theory intractable. Failing composable interfaces goes hand in glove with failing dynamic linking. Unmentioned until now is Rust's development experience. The compiler is legendarily slow, right down there with the likes of C++. And not only is that incredibly annoying during development, where it breaks your flow, but in my opinion, things that are noticeably slow can't be trusted. It takes ridiculous amounts of messing around to bog down modern hardware. More importantly, ideal open source package management is source distributed. For security, customization, cross-platform compatibility, dependency control, and especially local optimizations leveraging local SIMD architectures. It is depressing how much potential is lost in binary distributions, which basically cater to the lowest common denominator. The major obstacle for source distributions is compile times and obtuse build processes. C compilers are several orders of magnitude faster than Rust, but still not fast enough to comfortably distribute source only. We can do much better, and neglecting compilation speeds and duplicating code is an unwelcome barbarism. Programs getting slower seems to be a real problem nowadays. I think we'd all appreciate it if that stopped being normalized. As for the runtime performance, claims that Rust is as fast as C by virtue of offloading compilation to LLVM are overblown. Notably, FFmpeg, the cornerstone of multimedia, benchmarked a port and registered an unacceptable performance decline. I quote, FFmpeg is proudly written in the C programming language for the highest performance. Other fashionable languages like C++, C#, Rust, Go, etc. do not meet the needs of FFmpeg. It turns out that if a compiler generates an unholy amount of LLVM and then hopes it is magically simplified, things don't work so well. Rust rewrites also rather consistently drop GPL licenses in exchange for looser MIT ones. Probably they're just inheriting Rust's license without thinking, but in this way free software ideals are corroded. Businesses benefit, but the people lose since closed ecosystems can use free software and give nothing back. In other news, Rust has forced its way into the Linux kernel, but that appeal to authority is not the win some think it is when you realize Linus doesn't care much about Rust and hasn't bothered to learn it. he has stepped out of that issue and barely acknowledges problems. Admittedly, this has yielded some mad interactions in the kernel's mailing list, if you find that sort of thing funny. Fascinatingly, he seems to believe the process is productive. To quote him on Rust for Linux, if it were to become a failure, which I don't think it will, that's how you learn. Smashing endorsement there from the dictator of Linux who doesn't use Rust. It reminds me of a hilarious result from the 2020 Stack Overflow survey. Rust was the most beloved language, but most survey takers aren't familiar with the language. Low-level graphics programming requires GPU-side memory management. That operates outside Rust's abilities since it can't model protocols and state transitions, nor can it deal with cross-device ownership or temporal constraints. Granule's graded modal types would work better. Anyway, the problems of resource management are concentrated on the linearity side of the adjunction. Synchronization, for example, would be perfectly handled by session types. To evaluate Rust more personally, when programming in C, there are so many things I miss from the functional world, especially first-class functions, the mathematically motivated clean syntax facilitating function composition and thus code reuse, the extreme emphasis on purity, the safe concurrency, the rock-solid principled type system. From Rust, I miss nothing. The type system is a shadow of the Ocaml it spawned from. Memory safety doesn't materialize when the incomplete model can't accommodate optimal programs and steers you towards unmaintainable architectures. Weirdness abounds. Security is killed by static linking. Performance doesn't quite match C, and binaries are unpleasantly fat and slow to compile. The fact is, programming is about functions. There has to be movement, real computation, otherwise you're just shuffling things around. So focusing on memory is antithetical. It should be the last thing on your mind. Most code I write, even in C, is categorically motivated and designed for fusion. If it must save intermediate data to memory, then there is a morphism that drives the recursion and the memory operations from above. The logic is concentrated in non-recursive, pure stepper functions, in the style of recursion schemes that are easy to reason with, more optimal, and whose potential to go wrong is minimized. When memory must be touched in a significant way, it's almost always arena-based, and precise memory layouts are the last thing to work out, once the problem is understood. For example, hash maps are a single large array. Strings are extracted from an input file and may be interned sequentially. Most other constructions can be bump allocated. Abstract syntax trees for even complete programming languages can be flattened in memory, without wasting time or space dealing with pointers. There is always at least one branch that can be implicitly laid out next in line, or run length encoded. Obviously, the actual algorithm comes first, and memory layout remains flexible as long as possible. Pointers are only mandatory when interacting with the operating system. Otherwise, you'd rather have indices. The smaller the better, since halving their size doubles SIMD throughput, and structive array is well known to be a better layout than array of structs. They're better aligned, more composable, and more vectorizable. Industry has caught on, although they call it an entity component system. Finally, resource management requires linearity, or quantitative reasoning. The reason monads have been so successful and so abused in Haskell is to enforce linear sequencing. I/O is guaranteed unique because it can only be interacted with as a monad, and so the order of operations is well defined, albeit coarsely. Particularly regrettable is the missed opportunity to improve the ABI to use more registers and allow multiple entry functions, and especially to generate those automatically for case-split specializations. Skipping branches in this way would make specializing on argument shapes often completely free. I also wish for more control over binary layouts, for better locality, and to maximize multiple entry style fall-through for tail-called functions. In the end, I identified what makes Rust so uniquely irritating. In serious academics, research papers discuss existing literature. They motivate the new ideas with honest comparisons and conclude with limitations and directions for the future. Peer review forces this honesty, and it's jarringly missing from most Rust material. It feels dishonest and incompetent, and I'm sure it means well, but the result is barbaric. Rust is easily accessible, has massive corporate sponsors, strong marketing, works for many practical purposes, but is shallow, fundamentally broken, and proudly ignorant of a century of research. Is Rust better than C++? Sure, not even close. Is it better than C? That is less clear. It inherited all the mistakes of C via LLVM and gives you some half-baked functional features and a model of safe memory via regions. In exchange for slow compile times, fatter binaries, some bad OOP features, and a false sense of superiority. C++ is the favorite victim of Rust's aggression, probably because it can easily win. The most impressive figures are sourced from this comparison. But what is the prize exactly when the opponent's mascot is allegedly a diseased rat? Control of the sewer? If you want to argue about safety, then Rust is crushed by any typed functional language. Haskell, Ocaml, F*, PureScript, ReasonML, Scala, Elm, and especially by dependently typed ones like Idris, Lean, Coq, or Isabelle. If you want to argue performance, then SIMD and tight loops is better in C. Bespoke data structures cannot be modeled with regions, and neither can low-level linked lists or arenas. In industry, there are plenty of truly memory-safe languages, at varying performance costs, but the majority of the time garbage collection is not a bottleneck, and can be avoided with explicit memory or CFFI. So much was explored properly decades ago that repeating historical mistakes, and especially doing it in Ocaml, is basically a giant insult. Sure, Ocaml has a garbage collector and is unsuitable for obsessing over performance, but you could have been fixing that. My conclusion is not that Rust should be abandoned, but that it is a stopgap, shot full of holes that can only exist temporarily, with zealous backing and a misunderstanding of security and safety in the current void of ideal alternatives. As of right now, you can have real safety and performance by using, for example, Haskell and a CFFI, similar to what Python has been subsisting on for years already. But Haskell is much safer and can be very close to C performance if you avoid laziness and garbage collected objects. Meanwhile, we expectantly await a functional language to finally prioritize performance. Just barely distinguishable over the horizon is a type-directed equational system leveraged for fusion and automatically optimal memory management. Functional languages have all the information and all the potential. It is high time they started using it.